So in this video, we're going to talk about a new type of motion. This is circular motion. So we're going to consider objects that are moving in a circle at a constant speed. This is called uniform circular motion. So to start off with, let's draw our object moving in a circle. And there's lots of things that could do this. It could be planets orbiting. Oh, that's a really bad circle. Anyway, I'm going to go with it. So pretend like this is a circle. There's lots of things that undergo this type of motion. So it could be, a planet orbiting the sun, a moon orbiting a planet. It could be a ball with a string tied to it, spinning around a circle. And this is going to be at constant speed. And what I want to do to start off with is I want to look at the acceleration of this object as it moves around in a circle. So to do this, let's look at the velocity, because we know that acceleration is change in velocity over time. So if we look at the change in velocity that occurs, so here's our initial velocity, and maybe here's our final velocity. We're going to look at the change in velocity that occurs. Now, a few things about this. The velocity is always tangent to the circular path. So if this string were just to break, the ball, a lot of students need to think the ball will curve up this way or keep on curving this way. It would go off in a straight line. Okay. But, okay, so we'll sign it there. But let's look at this change in velocity. So we know that delta V is going to be my final velocity minus my initial velocity, and we're going to have to subtract these as vectors. And we talked before how it's kind of easier to think of this as the final velocity plus the negative initial velocity. Because then what we do is we take these two vectors. So we take the final velocity vector, pointing down this way, and then we add to that. So we're going to put this head to tail. We add to this the negative VI. So this is going to be negative VI here. And the resultant of that is delta V will be pointing in this direction. So that's going to be delta V for us. And if you look at it, that delta V is pointing towards the center of the circle. Okay, and therefore, because my acceleration has to point in the same direction as the change in velocity, we'll say the acceleration is also pointing towards the center of the circle. And as this travels around, you'll notice that the acceleration keeps on changing direction. And that's what makes this motion different than what we've considered so far. Thus far, the acceleration has always had the same direction. It could be either up the ramp or down the ramp. It could be along a table. Even in projectile motion, I'm going to change colors here. Even in projectile motion, what we noticed is, as the object was trailing through the air, it always had this downward acceleration. It's always pointing in the same direction. So this is something new, having acceleration that changes direction as the object travels around a path. Now, because this acceleration always points towards the center of the circle, we call it the centripetal acceleration. Okay, so this centripetal word, what that's telling us is that this is center seeking. Okay, so centripetal is center seeking. So this is a center seeking acceleration. It's always going to point towards the center of the circle. For reasons that we're not really going to go, I'm not going to derive this. If you want to know the derivation, feel free to look in your book. But we symbolize this with A sub C. So the centripetal acceleration, C for centripetal, is equal to the magnitude of this velocity. This velocity is called the tangential velocity. So it's going to be the magnitude of that velocity divided by the radius, this radius r, of the circular path. Okay, so this is one of the equations that you're going to be using a lot in this next unit, is that for centripetal acceleration. This just gives us the magnitude of it because the direction keeps on changing. But you square the velocity, which is in meters per second, divide by r, which has to be in meters, and that will give you the magnitude of our centripetal acceleration. Now, when talking about circular motion, there's the time it takes for one revolution. So if we have a ball traveling around a circle, or if we have a planet orbiting around the sun, it's going to take a certain amount of time to go around that circle one time. Okay, so maybe this is our sun. Okay, and then maybe this is a planet. And it's going to take a certain amount of time to go one time around the sun. And so, the time, let's say this, the time for one revolution, one time around the path, is what we call the period. So this is a measurement of time. For the Earth, it would be, it would be 1 year actually. It'd be 1 year. Okay, 365.25 days. It takes 1 year to go around the sun one time, and so that's the period of revolution. If this was a ball attached to a string, it might be something less. Okay, so, or at least I hope it's something less, or else that's a really long string. So time, our SI unit of time is seconds. So any period that we use will be in seconds. Okay, so the time for one revolution is what we call the period. Now, let's simplify things a little bit, and let's say we did have this ball attached to a string. Okay, let's go around in a circle, and let's say it takes 2 seconds to go around one time. We would say the period of revolution is 2 seconds. But we also might want to know, okay, how many times does it go around each second? That is called the frequency. The frequency is the number of revolutions or rotations, the number of revolutions per time. And again, we use seconds. So for this case, it would make one revolution every 2 seconds, or 1/2 of a revolution per second. And we don't really write revolutions per second. What we express this as is hertz. So we would say it has a frequency of 0.5 hertz. Okay, so hertz is units of reciprocal seconds, and that's what the frequency would be. Okay, so these are two terms I want you to know what they mean. Period is the time to go around one time, and frequency is how many times it goes around per second, essentially. So we can use this idea, and we can, we mentioned velocity when it came to centripetal acceleration. We can use this idea in order to get velocity kind of in a different way, because a lot of times you need to solve for that velocity in order to get the centripetal acceleration. So we'll have something travel around in a circular path, and when it goes around one time, it's traveled, say this has radius r, it's traveled one circumference around. So we know velocity is, at least the magnitude of the velocity, is the change in distance, okay, the distance traveled over time. Well, the distance that it has traveled is going to be 2 pi r. It's going to be the circumference of that circle. And the time it takes to go around one time is what we call the period. And we symbolize period with a capital T. Okay, so when you see a capital T, I know we keep on changing what these things mean. It used to mean tension, now it means period. But this is the period of oscillation. R is the radius in meters. So we can get our velocity using this equation for uniform circular motion. So again, we're making some assumptions here. We're assuming it's not changing its speed. We're assuming the radius is being kept constant the entire time. And if that is true, then it's going to have a constant magnitude of acceleration, which always points towards the center of the circle. And we can calculate the velocity if we know the circumference and we know the time it takes for one revolution of the period. So that's pretty much it for now. If you guys have any questions, please let me know.